Okay, I guess it's time to start. Good morning, everyone. Can you hear me? Yes, you can. Okay.
Yes, we can.
Welcome to the fourth class of the course Deep Learning by Example on Beowulf. This introductory course teaches the basics of deep learning and of different types of deep learning networks through a set of hands-on biological examples implemented in pairs, one example per class. Each class is supposed to be standalone. So for those of you who did not take previous classes, I will try to provide a background information which will be necessary and hopefully sufficient for understanding the contents of this class. This class is being recorded. For those of you who would not like your face to be in the recording, please make sure to disable your video. The class will expected to comprise two parts. The first part would be a lecture, which together with your questions and discussions, subsequent discussions will is expected to take approximately an hour and a half. But then, depending on availability of time, we will start do the second part, the practical part, where I will address your possible questions about the software. However, the software is pretty much self-explanatory. There is also software manual. So I assume that most of you should be able to manage the software on your own. And the last comment is that during the class, we will make two breaks after each 45 minutes of the class. So there will be total 2 breaks during the class. And that's it. So the topic of this class.
One second, Adi, can I just add one more thing?
Yes,
to the students, if you're not actually asking a question, can you please be sure to mute so that we don't get any other sounds in the recording?
Yes, I already mentioned, please keep yourself recorded, please keep yourself muted during the most of the class. After each slide, I will make a stop and ask if you have questions. If you do, please unmute yourself and ask a short question about the current slide or maybe previous slides. And let's postpone longer questions and discussions till the end of the talk, when we should have time. So the topic of this class will be generative adversarial networks and their application to bioimage synthesis. Let me start from first discussion of what is general adversarial network, or GAN. It is a composite network comprising 2 subnetworks, the generator and the discriminator. The generator network produces fake data or fake images from scratch or from noise, and it learns to trick the discriminator. The discriminator network compares fake data against the true data that are available and learns to expose the generator. So this procedure can be illustrated with simple example in order to get a better feeling on how this works. Let's consider a couple examples. In one example, a counterfeiter attempts to create fake dollar bills that look similar to the real bills issued by a bank. And a police attempts to determine whether the bills are genuine or fake, and gives a feedback to the counterfeiter. In this example, the counterfeiter is, of course, a generator, the police is discriminator, and the real bills issued by a bank are the data. In the other example, a forger attempts to create fake Leonardo da Vinci paintings, and a art dealer or critic makes an authenticity assessment of the paintings and gives the feedback to forger on what makes a Da Vinci looks like a Da Vinci. So in this case, the forger would be the generator, the art dealer or critic would be discriminator, and the genuine Leonardo da Vinci paintings will be the real data. In both cases, the generator initially will not do a good job of creating fake data, so it will not be able to fool the discriminator. However, given the feedback from the discriminator, the generator will eventually improve his skills and over time will produce better, more and more realistic fakes. In summary, the GANs, generative adversarial networks, have these features. First, they are generative models. The goal is to generate new synthetic instances of data that can pass for real data. And the second feature is that generator and discriminator are trained by pitting one against the other. Thus the term adversarial, which means antagonistic or confrontational. And the development of GAN was the most interesting idea in machine learning in the last 10 years, according to Yan-Li Kun, one of the leading authorities in deep learning. Being generative models, GANs are in a way similar to variational autoencoders we discussed in the previous class, which are also generative models. In particular, these two types of networks share some of the applications. For example, being trained on a data set of face images, both these networks can produce new images which were not there in the training data set. The biological example of GANs to be discussed today, called BioGANs application, attempts to create fluorescent microscopy images that show localization patterns of certain proteins in the yeast cell. These patterns encode important biological function. However, they cannot be produced experimentally for multiple proteins simultaneously at the same stage of a cell growth cycle. So this kind of synchronization of the images of the patterns can only be performed computationally using deep learning. Any questions so far? No questions. Then I proceed to the next slide. If you have question about this slide later, please let me know. So the application we will discuss today is the fourth of the examples to be discussed in this course, and it would be helpful to show the differences between this example and the previously discussed examples. The first comment is that it is unsupervised machine learning approach. In the first two classes we discussed supervised machine learning. The third one was also unsupervised, which means there is no labels for training that will be used for training. And the third one also did not use labels. The next feature is that it is a generative model functionally similar to variational autoencoder. I already mentioned that. Then it is a composite network comprising two subnetworks. From that point of view, it is similar somewhat to example of class number 3, where we also had a composite network, encoder and decoder. The networks in the GAN are trained interactively by playing a minimax game. We will come to it later in this class. And finally, there are multiple flavors of GAN, such as GAN, just regular vanilla GAN, then DC GAN, W GAN or Wasserstein GAN, and Wasserstein GAN with gradient penalty. And we will discuss these flavors in this class, but there are also more different flavors. Any questions? No. I proceed to the next slide. This slide will start discussion of the first of the flavors of GAN, called DC GAN. DC GAN stands for Deep Convolutional GAN. And this term, or this abbreviation, refers more to the structure of the network, whereas other flavors of the GAN, like Wasserstein GAN with gradient penalty, are more kind of functional. They refer to the particular algorithm that will be used for training a network. So for this example, for this DC GAN, I will discuss a simple example. Although our main focus in this class will be on image processing, for this example, I will use a sequence example. That will be sequence example. It will be a modification of the example we discussed in class number 2. And it will be instructive to understand the difference between the two examples. So let me first remind you the example of class number 2. So in class number 2, one of the examples, the motive detection example, was as follows. We generated randomly a set of sequences of zeros and ones, and assigned to each sequence a binary label, also 0 or 1. And the label was 1 or 0, depending on whether or not a certain predefined motive was present in the sequence. For that example, we use a motive like 3 ones in a row. And the purpose of the example was to train a certain network on this data, the sequences and the labels, so that the network will be able to predict labels for new, previously unseen sequences. Now I proceed to the description of the current example for this class. It would be basically similar to the previous example. We still have, we will be given sequences of zeros and ones, but this time, all of the sequences contain a motive. For motive, I will use longer motive like this, 0, 0, 1, 1, repeated 4 times, so total length will be 16, and the entire sequence also will be longer, not 10 characters, but 128 characters. So the main difference is that all of the sequences now contain the motive, and there are no negative examples. All the examples are only positive. In other words, all of the sequences contain the motive. And also there are no labels. So this example is actually more challenging than the example of class number 2, because we are given less data. We are not given labels, and we are not given negative examples. So the purpose of this example is basically to generate, learn. First, okay, we tell the model, here is a set of good data, good sequences, all of them are good. Figure out yourself what exactly makes all of these sequences good. In other words, what feature they have in common. It's up to you to figure out how you do it, and it's your business. But then generate us new sequences, which should also be good. So since this is more sophisticated task, we are given less data, the model for this task is also to be more sophisticated than the model of the previous example. So let's first again return to the networks, to the models. And I'll first start from the model we used in class number 2. for that purpose, for that example, we use this model shown here, which comprises tensors x, y, z, together with layers or transformations between the tensors. The transformation normally, like dense, for example, transformation, can be represented as a linear transformation of input tensor. In this case, it's y, with some bias and with some weights, plus nonlinear activation a, which is a. For that example, we used so-called sigmoid activation. And so what dense transformation is doing is basically computes a weighted sum of values of elements of the input tensor y, and stores the result, applies activation and stores the result in the output one-dimensional, zero-dimensional tensor z. And the values in z may be only between 0 and 1, because we apply activation, sigmoid activation. So value 1 of z would mean that the label is 1, or maybe it may be between 0 and 1, maybe rounded to 0 or rounded to 1. And if it's rounded to 1, that means the label is 1 for the sequence. So motive is present. If the value is 0, then it's no motive in the sequence. Now I proceed to the discussion of the model of the current example. So the entire network of the previous example will now become just one of subnetworks of our current model. It will be discriminator subnetwork. And we also need a generator. The generator is shown here. What it is doing is it takes a noise of certain length, then it performs a number of transformations. The most important part is the transposed convolution. We will discuss this kind of operation. And it basically doubles the size of the input tensor. Say from 16, we have 32, then 64, then 128. This is the final length of the sequence that we will generate with generator. The two networks shown here are examples of the deep convolutional network with DC-GAN. The term DC-GAN was introduced in this paper, and this paper provides a number of guidelines for generation of good, stable, good quality generative adversarial networks. As the guidelines include using convolutions and transposed convolutions in discriminator, which we did, and transposed convolutions in generator. Instead of max pooling or upsampling layers, those layers were discussed in the first class. Use batch normalization layer. It's basically doing normalization of each particular tensor by making its mean value close to 0 and standard deviation close to 1, and avoid fully connected hidden layers in the generator. Any questions so far?
There's a question in the chat. How
Okay.
is this considered unsupervised learning if you still need training examples to use for the discriminator?
It's training examples, but they include only sequences, not labels. So we do not have labels, and that, from that point of view, it is unsupervised, because supervised would assume that we have both sequences of both data and labels assigned to the data. But in this case, we don't have labels. Any other questions? No. I proceed to the next slide. If you have later a question about this slide, let me know, please. This slide discusses the transposed convolution transformation. We did not discuss it previously in the previous classes. So let's see what this transformation is doing. But I will first remind you the regular convolution, not transposed, but regular convolution, what regular convolution is doing. And it would be a more simple to explain this operation with two-dimensional data on images, because easier to visualize. So what normally convolution is doing is it takes, we have input image and output image, and we have a filter or kernel. We slide that filter over the input image, and at each position of the filter, we compute a weighted sum of pixel values plus a certain bias, and then apply possibly some activation like we did in the previous slide for the dense layer, and assign the result to the corresponding pixel of the output image. And this operation involves a number of different hyperparameters. The hyperparameters are the constants that they're not just adjusted automatically by the training procedure, but should be set by us researchers. And the hyperparameters, the most important of them is probably stride. The stride is the step that is used when we slide a filter over the input image. In this case, the stride is 2, because every time we jump across 2 pixels with filter. But there are examples of convolution. Another example shows also a regular convolution with stride 1 when we jump to on 1 pixel. And another important parameter is padding. Padding is showed by how many pixels the filter goes beyond the original image. In these two cases, padding is 0 because the filter does not go beyond the input image. But the third example illustrates the case where the padding is 1. So we go by 1 pixel outside of the original image. All of these hyperparameters, the input and output size, the size of the filter, which is K or kernel size, the stride and the padding are not completely independent. They are linked one with another. Basically, the size of the output is uniquely defined by the previous 4 hyperparameters. And that is reflected by this relationship. This kind of equation that links all of the hyperparameters, and you can check as a home exercise that this equation holds for all the 3 examples in this chart. Now I proceed to discussion of transposed convolution. Now let's ask a question. I return to the first of the examples. We have here the input image of size 5 by 5 and the output image of size 2 by 2. Can we do the opposite operation? Can we produce a bigger image from the smaller? In other words, make Y as input and X as output. And the answer is positive, and the corresponding transformation is termed transposed convolution, and it can be performed as follows. We first take the output image, which now becomes an input, our input. We create gaps in the input image. The gaps of the size, the same size as was the stride in the previous example. So in this case, the gaps of size 2, each 2 pixels now separated by 2 pixels. And then use a regular, like we do regular convolution with stride 1, and swap all of this, these pixels. And we produce the image of, the result will produce image of size 5, the same as for, it was input for the previous example. And the 5, now the hyperparameters of the stride, of the transposed convolution, which is also, by the way, called deconvolution sometimes, they are shown with primes, and they are also linked with a certain relationship like this one. So the size of the output is still uniquely defined by all the previous hyperparameters of input. And in Keras, the transposed convolution is performed using a certain class. This is a constructor for the object. You create an object every time, and it takes the parameters similar to those taken by regular convolution. So the first parameter shows how many transposed convolutions we perform. So if we have initial input, some image, then the output will be a stack of deconvolved images, not just one, but a stack of, oh, actually, in this case, it will be 10, sorry, because it's 10, there should be 10 here as well. And the second positional argument is the size of the filter used to perform transposed convolution. And there are other parameters. In Keras, the zero padding is also called valid padding, and the non-zero, when we have the same sizes of the input and output image, is also called same padding, just Keras terminology. Any questions? No questions. This slide starts to discuss the code for the simple example we just described previously. We mentioned previously that any program in Keras comprises 4 major steps of processing. The header, getting data, defining a model, and running the model. The second and the third step may be swapped. So for this slide, I discuss the header step and defining the model step. So the header is normally, it's a set of import statements. We import general Python packages. We do import NumPy and TensorFlow. And then we import some particular Keras layers and optimizer and yes, layers and optimizer, and sometimes something else. Then we, in the defining the model, we employ the so-called sequential construct approach, where each model is initially defined as an empty container, and then we sequentially add layers to that container. And this approach is used to build the discriminator model, then generator model, and then the composite model, which we call GAN. So what is important to mention here is that the discriminator model has a sigmoid activation as the last layer in the model, which means it will output the values between 0 and 1, just because of sigmoid activation has values between 0 and 1. And this output from the discriminator can be interpreted as a probability, because it's between 0 and 1. And that would be the probability that the input data is good. The second comment is that the generator also has sigmoid activation as the last layer. But that's for different reason. That's because the generator will produce, in our case, sequences of zeros and ones. So it will output something between 0 and 1, which will be subsequently rounded up to the nearest integer. So the output will be a sequence of zeros and ones. And finally, important comment about the GAN, the composite model. For GAN, we use also sequential construct approach, but instead of adding individual layers, we now add the entire model. For GAN, we first add a generator model to GAN, and then we add the discriminator model. And so because the discriminator will be the last step of processing, data processing by GAN, the output from GAN would be the same as output from the discriminator. So the output can be interpreted also as a probability, the probability that the input, whatever it is good. The second comment is that since the generator is the first step of processing by in the composite network, the input to the GAN would be the same as input to generator. In other words, it would be noise, random noise. And the last comment is that before we add a discriminator to the GAN network, we freeze the weights of the discriminator. This statement, detrainable is false, means that we do not allow the weights of discriminator to vary when we train the GAN network. So when GAN will be trained, only the generator weights will be actually adjusted. That's it about this slide. Any questions? No questions. I proceed to the next slide. So this slide discusses the last two steps of processing by the simple model. First, it's getting data. How we get data? We first generate 1,000 of completely random sequences of zeros and ones, and then we substitute 16 randomly selected characters at random position in each sequence by our predefined motif of length 16. So each sequence will contain a motif, the motif that I showed previously. And that's how we generate the data. Then we perform training of the model on this data. And the training performs, it's a number of epochs. We run through all epochs. And then for training, we use a function train on batch. This is a new kind of method that we did not use in the previous classes. In the previous classes, we used two different methods for training. It was just train, or it was train generator. For this, for both train and train generator perform the training of the entire model for a number of epochs, just one command. But for this example, we have to use train on batch, which performs one step of training basically for one epoch only. And the reason why we use train on batch here is that generally the training of discriminator and of generator should be iterative. You cannot do basically in general do training of one only discriminator through the end, and then do training of generators through the end. But you perform a certain number of iterations of discriminator, then a certain number of iterations of generator, and that would complete only one epoch of training. So you do iteratively one, then another, and then you repeat new epoch, and then again perform a certain number of iterations of discriminator and generator. So when we do training, that's the expressions in the boxes, means that we first train discriminator. We on real data, if it's real data, then we require that the discriminator will output once, because that's good, considered good data. When we train on fake data, the discriminator attempts to output 0. That would be, the weights will be adjusted so that it will output 0. And when we train GAN, and GAN is basically only generator weights will be adjusted during training GAN. The discriminator weights will be frozen. Then we, on fake data, we attempt to create one. Any questions about this one?
There's a question in the chat. Why is the discriminator not trained, and how will it learn to discriminate?
The first one, why discriminator is not trained?
Yes, that's right.
It is trained. Why it is not trained? It is trained. The discriminator, oh, you mean the generator, maybe?
Georgie, you can unmute yourself and ask the question if you like.
Okay, yeah, sure. So in the prior slide, you mentioned, you said that the discriminator trainable equal false. So this means it won't update its weights, right?
Right. Yes, I understood now the question. Okay, so it is the weights of discriminator are frozen only when we train GAN, this one. But the discriminator just itself, when we run discriminator, the weights are not frozen. If we return to the previous slide, let me go to the previous slide now.
I think I got it. So you mentioned like you only set the discriminator equal false only for get again one, but not for.
Let's see. We do detrainable false only when we build GAN, right? But before we did that, we built discriminator. We did not require here that the weights are frozen, and we compiled the discriminator. That's compiled means we completed the model for discriminator. So we did not require that the weights of discriminator are frozen at the step when we train discriminator itself. Does that answer your question?
Yeah, it looks like something in the semantics when you did then d.trainable equal false. That basically
that's true only for when we train GAN, only here. Before that, before this line, we did allow the discriminator weights to vary.
I see. Okay, thank you.
Okay.
Also, like, you know, when you train, I mean, it's kind of interesting. You train a batch on real data and then a batch on fake data. So usually you have a batch of, you know, all the classes you have in a given training epoch, right?
Of different what?
Of different classes, right? Here you have two.
Oh, classes. That's right. Yes.
Yeah.
In general,
I mean, how does that even, you know, help or not help? I mean, why you don't just like mix them up together and train, you know, with real and fake data into one train on batch call?
I'll explain it. We will come to it later in a short while. I will talk about it. Okay. For now, we just have one data set. Like all data are similar. All of the sequences have the same motive. So for now, it's just one type of data. But when we have more than one type of data, it's a different story. But I will come to it in a short while.
Okay, thanks.
Okay, and if there is no more questions, I proceed to the next slide, which discusses the so-called the GAN optimization objective. So far, we consider training of the GAN as just a set of steps, like trained on batch, performed in a number of epochs. But let's now look what we actually optimize during these steps. And it turns out there is a well-defined optimization criterion that we actually optimize during the training. And this slide will discuss that minimax criterion. To this end, I will first rewrite the relationships from the previous slide with slightly different form. So we said that when we try and train a discriminator on real data in this case is X, we wanted to output ones. When we try to train a discriminator on fake data, the fake data will be Z, where Z is noise. we want to output 0. And when we, we try, when we try, basically it's a GAN. GAN is discriminator, then generator. And when we train GAN on fake data, then we want like to output 1. Now I can rewrite these 3 relationships in a slightly different form. If we want the discriminator to tend to 1, which is a maximum value for discriminator, that is equivalent to requiring that logarithm of discriminator should be maximum, because logarithm is increasing function of its argument. When we require that discriminator tends to 0, then it's equivalent to requirement that logarithm of 1 minus discriminator tends to maximum. And the last equation relationship is equivalent to minimizing logarithm of EDs of 1 minus whatever is produced by the discriminator and generator. So in this relationship, I show in color those weights that are adjusted at the step of doing maximization or minimization. And those weights that are not trained are shown in black color. And this 3-letter relationship now can be rewritten as a single relationship, which is called the minimax optimization objective. Here we minimize this expression with respect to generator weights, but we maximize with respect to discriminator weights. So it's basically equivalent to this 3. And this, we will have to make stop. I will finish this slide and then we will make a stop. This relationship allows a nice geometric interpretation, which is different from training of regular deep learning networks. In the regular networks, we normally, when we train networks like the networks of the first 3 classes, we minimized a loss function as a function of all weights of the network. I show only 2 weights here, but basically we consider all possible weights of the network. And we find a minimum of that function. In the adversarial training, its picture is different, and it will be easier to explain it using this surface, which have a saddle point. So when we minimize, and we have 2 sets, not 1 set of weights, but 2 sets of weights, the weights of generator and the weights of discriminator. When we try to say minimize this criterion with respect to generator weights, that means we fix the discriminator weights. Fixing discriminator weights means that we will stay within a hyperplane which is perpendicular to the this red axis, but we will move in this plane. We will vary the generator weights, and the intersection of that plane with our minimax surface will be a curve with minimum, and that's what we try to minimize. We try to find a minimum of that curve, but we perform only 1. We do not go all the way to the minimum. We just do 1 iteration only per epoch. Then we proceed to the maximization step. In the maximization step, we vary only the discriminator weights, which means we will be in the plane, in the hyperplane, which is perpendicular to the generator axis, and the intersection of that plane, this one, with this surface would be a curve with maximum, and that's where we try to try to find the minimum. But again, we do only 1 step of minimization, and then we switch again to one step of maximization, and then we switch again to minimization of the using the generator weights. That's basically how it works. Any examples or any questions?
Are you guaranteed to find it at they intersect at a saddle point, or they can the optimization might not always reach a saddle point? That would be the same saddle point for both curves.
In practice, usually we never reach the saddle point, but if we do, theoretically we can, and that would be basically, if you can see that it will correspond to discriminator 1/2 in both cases, and that would be a kind of by analogy with game theory. It could be a Nash equilibrium, because we have two players, and if we ever reach the saddle point, then no further changes would be performed. We will just be frozen. But in practice, we never reach that point. It may be most cases, maybe oscillation somewhere around, some kind of dynamic equilibrium.
Oh, thank you.
Excuse me. So up to the equation, so the dxwd, you try to maximize it to 1, right? So in this step, you only optimize WD.
WG, you said, right?
No, I think you colored. I mean, on the top.
Oh, this one.
This one, yeah,
right,
this one.
okay.
This step you only optimize WD, right?
Yes, the weights that are adjusted at a particular step are shown in color, and the weights that are not adjusted are shown in black. Like in this case, just yes, WD only. It's shown in red.
I think for the second row, yeah, the next row, even you have WG, weight G, and the weight D, both in the equation, you only optimize weight D.
Right. Right.
Okay.
In this case, we also optimize D, right? But it's different kind of data. In the first case, we use real data, substitute real data into the discriminator. In the second case, we substitute the fake data, which is generator applied to noise. So this is the entire thing is fake data. So on different data, we apply a discriminator on different data. This is why we are able to do both this independently, because it's different data.
Okay, got it. It's different data.
Right.
Okay. Thank you.
You're welcome. If there are no questions, we can make a stop, 5-minute stop. We're already a little bit out of schedule, but anyway, let's meet again maybe in 5 minutes or something, and we'll continue. Okay, it looks like it's 5 minutes approximately past, so I will continue with the next slide. So this slide discusses the mode collapse. It's one of the issues that typically occur when we do training with GAN. So far, we discussed one type of data. That was a question, how do we do, what do we do when if we have multiple different types of data? So the mode collapse is an issue that may occur in GANs when there are more than two or more different types of data in the training data set. And the issue is that the generator can find a single type or a particular type or a few types, a subset of types of data that it can use to fool the discriminator. And in this case, if the original data distribution had two types, like two modes shown in the two maxima in this chart. Here, Y is a certain feature that parameterizes different types of data. So different types of data have basically different value of that feature. But the blue curve corresponds to original data. But when we train a model on that data and generate new data, then that data will contain only one of the modes. And this is basically what is mode collapse. The second mode is collapsed. To illustrate that phenomenon with a simple example, I used the same example exactly as we discussed previously, but this time I will use two different motifs shown here. They both have size of 16, but the second motif is 0, 1, 0, 1, 0, 1, alternating total is 16. And each sequence in the training data set will contain only one type of motif. And if we train GAN on this data, we will have, can then generate the new data by applying the method predict to the generator. We will output this result. In the blue bars here show the number of sequences in our data, in our training data set. So we designed the training data set so that it will have 40% of sequences of the first type and 60% of sequences of the second type. And when we produce generated data, we will observe only 133 sequences of the first type, but more than 900 of the second type. In other words, we have here partial collapse. The first type of sequences will be produced in a small amount. And also the sum of the generated sequences exceeds 1,000, which means some of the generated sequences will have two motifs. Any questions about this slide? There was a question previously about what do we do with different types of data. Does this slide address the question? Okay, I move to the next slide. This slide describes how we can run simple examples on BioWolf. We first allocate an interactive session, then we load the module dlbio/class4, and then there would be two executables available. The simple GAN executable, that's executable for the first example, and the mode collapse executable for the second example. And we run those examples just by typing their names. And we get, in the first example, we say we generate, when we generated, after training, we generated 999 sequences with good sequences with motif out of 1,000. So it's only one sequences for some reason was not produced. It did not contain the motif, and that's for one of the motifs. When we run the second example, we have initial input training sequences in the training data set, 400 sequences containing motif of the first type, 600 sequences containing the motif of the second type, and in the output, in the generated sequences, we have 133 containing the motif of the first type and 905 of the second type.
I mean, what if there were like 50-50, will like, how does it pick which motif it will like, you know, generate more of?
Yeah, normally the collapse is the minority mode. The dominant mode is normally what generator keeps producing. But if it would be 50-50, actually I did not try, but you can try it yourself at home. If you change, it's easier, should be easy to change the code. And that's a good question. I don't know which one would be preferred in this case by the model.
Okay, maybe most probably we'll randomly pick one.
Say it again.
It might randomly pick one of them.
Yes, yes, exactly. And I'm not sure which one would be picked. The one that is easier for generator to use in order to fool the discriminator. But which one would be, I actually didn't try. But that's a good question. It's a reasonable question. So it should be very easy to change. You will see the code, you will have code available. So you will see which one would be generated then.
Okay, thank you.
Any other questions about this introductory part? This is the last slide of the introductory part. Now we proceed to the discussion of biological example. Okay, now I proceed to the biological example of this class, which is called BioGANs, and it deals with generation of fluorescent microscopy images that visualize localization patterns of certain proteins, which are important for developmental biology. In this example, we will be dealing with images of fish and yeast cell, and the images, all the images will be two-dimensional. There are two channels, the green channel and the red channel. The red channel always correspond to the same protein, BGS4. And this protein is a growth marker. This distribution shows basically from the distribution of this red protein in the cell, the expert in fish and yeast can figure out the stage of the cell growth cycle. So it is strongly connected to the growth cycle. The distribution of the red channel is strongly connected to the growth cycle of the cell. As for the second channel, there would be a number of, basically it's also one of the so-called polarity factors. There's a number of such proteins, total 41, but we will focus only on these four. And the polarity factors determine the geometry of the cell. So the biological task posed by researchers was how different polarity factors interact with one another. And to solve that task, ideally, they would need to see the distributions of all these polarity factors simultaneously at the same stage of the cell growth cycle. However, this distribution is not possible to produce experimentally due to technical difficulties. Every time you do cell only with one green signal, and of course, cells with different green signal will correspond to different stages of the cell growth cycle. So the computational task was to train again on available data and generate synthetic images that show this localization of this time multiple polarity factors simultaneously at the same stage of the cell growth cycle. In other words, we would like to output the model to output a synchronized distribution of the polarity factors, multiple polarity factors in one image, or maybe, in one picture. And that task cannot be performed experimentally. It can only be solved computationally. The data for this example it's called localization interdependency network data set. Will be discussed later in one of subsequent slides. It's plenty of data, but every time we have only image only with two channels. And the code for that example is available was available on GitHub, implemented in PyTorch, but for this class, it was re-implemented in Keras, and basically includes 3 executables. Any questions so far? No. Next slide gives a quick overview of the BioGAN code, and only shown here is only the main function of the training executable. But that main function manages execution of the entire program, and it involves the same 4 steps that any Keras program does, that including the header shown here, the getting data, defining the model, and running the model. And of course, this is part of only highly simplified. There are a number of other stuff. It's only the very bottom of the entire program. There are a number of other functions in this code. So they are kind of in the top of the program, are not shown here. But we will go through discuss main of these functions. In the subsequent slide, we'll first discuss what data I used for this example, the lean dataset. Then we will discuss the different architectures of the model, DC-GAN, DC-GAN separable, and DC-GAN star shape. And we will discuss different algorithms for training the model on this data, such as traditional GAN, or also called vanilla GAN, Weserstein GAN, and Weserstein GAN with gradient penalty. And we also touch base on the optimizer, the particular algorithm that will be used for the minimax optimization RMS probe. Any questions? No. So the data, this slide presents the lean data set. It all comprises two-dimensional fluorescence microscopy images of fission yeast cell. Each cell is of length between 7 and 14 microns, depending on the age of the cell, and the width is approximately 4 microns. There are two-channel images. Size of each image is 48 by 80 pixels, where 1 pixel corresponds to 100 nanometers approximately. I already mentioned that the red channel will correspond to the BGS4 protein, the growth marker, whereas the green channel will correspond to, in this data set, it's 41 different polarity factors, but we focus only on 6 polarity factors, and those 6, for those 6, we have 20,909 images in total. So it's plenty of data. Any questions? No. Okay. This slide presents the DC-GAN model for the biological example. This is the most basic model implemented as a part of this application. And it comprises the generator and discriminator. The generator network starts from a noise of size 100. Then it performs a number of transformations of that noise tensor. First, it creates a rectangle, so it's shown here. Basically, the tensors, the intermediate data tensors. The first tensor, for example, comprises images of a stack of images of 3 by 5 pixels, and the number of images in the stack will be 512. Then subsequent transformation doubles the size of image. Now it will be 6 by 10, but the number of images in the stack reduces twofold. And then again and again the same. And finally, we arrive at a two-dimensional image of the normal size, 48 by 80 pixels with 2 channels, like was described in the, like it's supposed to be. And the discriminator network is performing a kind of opposite operation. It starts from a 2-channel image, then it performs a regular convolution. It reduces the size of image by twofold, say convolution with stride 2. So there will be a stack of 64 images of size 24 by 40. Then again and again the same operation. And at the end of the network, we have a sigmoid activation, which means it will output a value which can be interpreted as a probability, a value between 0 and 1. And value of 1 means that the image is good, the input image is good. Value of 0 means it's not good. This is the most basic, as I mentioned, model to be discussed in this example. And subsequently, we will make improvement to both generator network and the discriminator network. And this particular model is pretty sophisticated, but it's actually not very useful. First, because it produces the two-dimensional, only 2-channel images, which can be produced experimentally. And also, even this model trained on all the available data will not be able even to generate all the green channels because of the mode collapse issue. So if we train this model on all available data, only a subset of channels would be generally generated by this model. So it's not, basically, it's not useful. Now let's look at how we can improve this model. By the way, any questions about this slide?
I kind of thought that you will generate 6 green channels, 1 channel per protein, right? So your output should be 48 by 80 by 7, one for the red channel and one for and
No, not for this network. This one cannot generate 7. That would be that require improvement of the generator. This network outputs only 2 channels.
but then what the green channel will include which protein in this case?
It will include whatever it will be basically random. If you train this network on all available data, and then do generation, then it will basically pick at random whatever polarity factor is available and will generate image with that polarity factor.
Okay.
But even not all of the polarity factors could be generated this way because of the mode collapse issue. So this model, even though it is pretty sophisticated, but it's actually very limited in terms of its capability.
Right, because if I understand correctly, your objective is to generate the 6.
That's right. That's right. That we will discuss. That we
Okay.
plan to discuss in the next slide. That's kind of improvement we want to make to this model. So this model is most basic model that is still considered. If you do not want to output all the 6 different polarity factors, you can still play with it. The advantage of this model is that it's trainable very easily. You can, just to see how it works, you can run on, say, train this model on a subset of images and see if you can produce 1 channel. But it's not very useful for our ultimate goal. Any other questions about this? Now, let's consider the next one. This slide will address your question, and it would be actually presenting the main theoretical contribution of this entire BioGANs study. That contribution is the so-called DC-GAN star-shaped model. But before we proceed with that, let's first talk a little bit more about the generator model of the previous chart. That's the same. We're talking now only about improvement of generator, not discriminator. Discriminator will be discussed later. But now we focus on the improvement of the generator network. And the network shown here is basically the same generator as I showed in the previous slide, but redrawn in slightly different form. Here, the data flows from the bottom up. At the bottom, we have input noise of size 100, and then through a number of transposed convolutions, we generate new tensors. You see here 3 by 5 pixels and a stack of 512, the same as in the previous slide. And then another twice bigger image, but with twice smaller stack, and so on. And eventually we arrive at the green two-channel image. So once again, what are shortcomings of this network? First of all, so of course we cannot generate multiple green channels, as you mentioned. That's correct. We can generate only 1 green channel. Another important shortcoming is that the two channels that we generate kind of have equal rights, the green and the right channel. They are not there is no interdependency between these two. But what we ideally would like to do is to make the green channel dependent on the red channel, because it is the red channel that determines the stage of the cell growth cycle. And if green is dependent on the red, then the green will come at the same stage of the cell growth cycle as the red channel. And the star-shaped architecture will address both these issues, but the easiest way to present the star-shaped architecture is first to discuss the so-called separable architecture, DC-GAN separable, which is a kind of rudimentary version of the star-shaped architecture. Let's first consider that separable and see how it differs from the regular DC-GAN architecture. In the separable architecture, we first, the noise is split into two portions. Instead of using 100, we use two of size 50. And each of the portions is used to produce a separate channel, the green channel and the red channel. The red channel is produced independently from the green channel completely. But generation of the green channel is dependent on the red channel. It is influenced by the red channel by this concatenation transformations. You see, at some point we do concatenation of the red tensor with green tensor, and then again later on another concatenation. So in summary, this allows us to expect that the green channel will be at the same stage of cell growth cycle that as the red channel. And the red channel, basically, when we generate, would be random, but at least the green channel should be at the same stage of growth cycle. And the star-shaped architecture is very similar to separable, but instead of one green channel, we will use 6 or however many we want to use. So red generation of red channel is still independent of any green channels, but every green channel would be dependent on generation of the red channel. So what is, in summary, what is special about that star-shaped architecture? Of course, because each green channel is trained to be dependent on the red channel, there is a reasonable expectation that all the green channels will be synchronized, and they will come at the same stage of the cell growth cycle, which is determined by the red channel. Although the red channel will correspond at random, it will be a randomly generated growth stage of the growth cycle, will correspond to random stage. We cannot predict what stage would be to random, but at least the green channels, all of them, will correspond to the same stage of cell growth cycle. In other words, they will be synchronized, and that's what we wanted to do, basically, at this moment. Any questions?
It's me. So I don't understand how you can concatenate the red channel to the green channel, so they become dependent.
Concatenation operation is basically, it was, I don't have a slide specifically for concatenation, but basically it's kind of, you have one tensor and you have another tensor, say these two tensors, right? And then you create concatenation, means you create a sandwich. This tensor would be here underneath, say, for example, right? So this tensor, for example, 12 by 30, and you have 64 images in the stack. The size of stack is 64. And this one is the same, 64. By concatenation means you'll create a sandwich of these two tensors where the size of images will still be 12 by 30, but the size of stack will be 128, double the number of images in the stack in this case. So concatenation is what is I just described. And then you proceed from that concatenated image, and you do continue to do what you're doing, what this network suggests.
Yeah, so you do the upper convolution. So the upper convolution will simultaneously convolute both the red channel and the green channel.
Actually, after concatenation, we just have a tensor of will be stack of 128 and a tensor. Then it will be there is no green and no red at this point. Actually, they are shown in the chart, but actually it will be just some tensor. And then, yes, it will perform transport convolution of deconvolution of the entire stack, and it will produce a specified number of the and the new image. If we specify to produce stack of size 32, this is a parameter. The number of images in the stack and the output of transpose convolution is a parameter of transpose convolution. We can specify whatever we want. I discussed it previously in the previous slide. I mean, in one of the previous slides. Yes. So basically, yes, we use a concatenated, but to produce the next tensor of the green channel.
But initially, both the red channel and the green channel, the 1 by 1 by 50, it's just generated from a Gaussian distribution, random number.
Yeah, for example, Gaussian, yes. It's random number, yes, random number.
Just like this 50 random Gaussian distribution number.
Right, right.
It has no any relationship with the real data.
To what?
To the real data.
Oh, to the real, no, it's completely random. It's noise.
Okay.
But
okay.
Somehow it will be less and less noisy. Well, there is still noise because when you generate image, that noise will affect what phase. Say, for example, for red, right? It's also the same. Red is also produced from the noise of size 50. Because you have input as a noisy input, you will generate final image. Not all the time it will be the same image. It will be different image at every step of generation. If you generate once, you get one red image. If you generate make second attempt of generation, we will generate a different image generally. It will correspond to different stage of cell growth cycle. And that's how noise will affect the output. But it will look like realistic good image, but just corresponding to different stage of cell growth cycle.
Okay, thank you.
You're welcome. No more questions? Okay, so we discussed the improvements that were made to the generator of the BioGANs network in order to allow generation of multiple channels simultaneously, multiple green channels, and to make sure that those channels will be synchronized. They will will correspond to the same stage of the cell growth cycle. Now let's look at what kind of improvements were done to the discriminator network. And the discriminator, it's a GAN, or basically the discriminator network may have issues. The issues is called vanishing gradient when basically the training procedure stops and no more training. You do not see any improvements in the training and the loss function. And that issue was partially discussed already in the second class for sequence data, but it's attributed normally to this sigma layer as a last layer of the discriminator network. So if the sigma layer, you see it's like sigmoid activation, it's at very large, very small values of its argument, it goes to saturation where the derivative is close to zero. So when we do training, we compute gradient of the discriminator network. And the gradient, as you can see, would be proportional to the gradient of the derivative of the sigma function. And since the derivative may tend to zero at some values of argument, then the entire gradient of discriminator will also tend to zero. So that is the reason for issue. It's one of the issues that often occur when training gets. So the for that purpose, to address this issue, another version of algorithm of GAN training algorithm was proposed, which is called Wasserstein-GAN. The idea of Wasserstein-GAN is get rid of the sigma layer, and the remaining part of the discriminator, the entire discriminator network before the last layer is designated F, and we replace now D with F, and the remaining part is renamed now to critic. So it's no longer discriminator, it's critic. It's called critic, and it will not output values between 0 and 1. It will output any values, will be positive, maybe negative, maybe any value, theoretically. We call it score. The critic outputs scores, S. And since we do not output the value between 0 and 1, which can be interpreted as a probability, we can no longer use the binary cross entropy loss function that could be used by the discriminator before we remove the sigma layer. We need a new loss function for that purpose. And as a new loss function, the authors of this paper proposed the so-called F-movers distance, or EMD. This is a distance between the distribution of critic scores generated on the real data and on fake data. And let's see, so that EMD was used as also called Wasserstein loss function. It's a minimum, it's defined as minimum work required to transform one distribution to another distribution. And now I will describe how that minimum amount of work can be computed. First of all, we have two distributions of scores. How we compute that? We can run the critic on a number of real images, produce a number of scores. From each image, we produce one score, but we have a data set of data images. We can now compute a histogram of scores, bin the values of score into several number of bins, and then build histogram and normalize the histograms. We eventually will arrive at the probability distribution of different scores for the real data. And the same, likewise, we can do for generator, for fake data produced from noise by the generator, and also generate some distribution of scores. And as I said, the new distance as a new loss function, the authors proposed Earth-mover distance between these two distributions. How can we compute the distance between two distributions? You can think of those distributions as two piles of Earth. The work, the Wasserstein loss, or EMD, would be the minimum amount of work to transform one of these piles to another pile. And we can do it by, say, taking a piece of this pile and moving it to the second distribution. The distance would be, this would be the distance to which we moved. And the work to move this pile of Earth would be equal to the distance of distance we used to move and times the mass, which is the area of this small pile. And so this way we can move all the entire distribution to the red one and compute the total minimum amount of work to transform one distribution to another. In general, of course, it's pretty sophisticated operation. It's a non-trivial computation, but there is luckily a simple formula that can be used. It's approximate formula that can be used when the two distributions are more or less similar, not too far different. And that formula is shown here. They basically, for Wasserstein loss, the formula would be minus expectation of the product of the two distributions. And according to that formula, we need basically to minimize Earth mover distance, which means, because that's minus sign, we basically need to maximize an expected value of this expression in the square brackets. And let's see when this expression will be maximized, when it will have maximum. It will have maximum when the two distributions will have maxima at the same positions. So in other words, this maximization will force the two distributions to have maxima at the same locations. Indeed, if, for example, one distribution has a maximum and the other distribution at the same location has minimum or zero, then the product will not be big, will be the product of maximum value times, say, zero will cancel out. And but if the two distributions have simultaneously maxima at the same position, then the product of two big numbers will make significant contribution to the entire value in the square brackets. So it will help maximize the entire expression. That's basically an approximate formula which we use for Wasserstein laws. Any questions?
So for the binary cross entropy loss, so in the equation, what does it mean, the W, PIW?
So in the binary cross entropy loss, you can look at class number 1. We discussed it in details, but basically when we compare the Y's it's basically for labels. We have some theoretical expected values of whatever output of a network, they are designated Y, and P, I, W are predicted values, predicted by the network. So we compare the output from network, which is predicted by network and which depends on the weights in the network, with the expected, the target values of the network. And we try to adjust weights to make the predicted values as close as possible to the expected target values. Does this address your question?
Yeah. So YI is the target value, and the PIW is the weight, P is the probability.
Yes. Well, probability, because it can be interpreted as a probability because we have the output from discriminator, it will be between 0 and 1, so we can interpret it as a probability.
Thank you.
Okay, well, if there is, we can discuss it later. If you still have question, we can discuss it after the talk in more details. And the next would be, I'll describe here a couple of features of WGAN. This is when we get rid of the sigma layer, we replace with discriminator with critic, and also the new loss function. But there are other features proposed by the authors of WGAN. Those features will be discussed in the next slide. This slide also will discuss a next modification of WGAN, the Wasserstein GAN with gradient penalty. So the basic question that we have, after we remove the sigma layer at the end of discriminator and make it critic, now the output from critic, the score, may theoretically be unlimited. And of course, we will not have, in this case, the vanishing gradient, because the output is no longer limited by 0 and 1, but we may have theoretically unlimited gradient, exploding gradients. That's another possible issue, which may result in instability of our training procedure. So how can we avoid that exploding gradients or instability in the network? In the regular vanilla GAN, we don't have that instability, as I mentioned, because we have sigmoid layer, which will limit the output values. But once we remove the sigmoid layer, in the GAN, we can take care of the large gradients by clipping the weights of the network. So each layer transforms the data, the input from the input tensor by first performing the linear transformation plus nonlinear activation. And if we limit the weights in this network with clip, the suggestion is to clip, which means if the weight is beyond a certain interval, then we set the weight to the boundary of for example, if the weight is very negative, then we reset it to minus C. And if it's very positive, we reset it to plus C. And the suggested value of this boundary of this interval is C. The boundary value is 0.01. So basically, clipping means that we readjust the weights of the network after each epoch, which is pretty expensive operation, but it works in practice. At least it allows us to avoid this instability. Yet another feature of WGAN is to use, the suggestion of the authors is to use RMS probe optimizer for training a model. We will discuss the RMS probe optimizer in the next slide, what this optimizer is doing. And the ultimate goal of clipping, of this clipping procedure, is to keep the gradient within certain limits. Like in this chart, we show the curve should always be in this shaded pink area, which means the gradient will always be limited. The absolute norm of gradient will always be limited. More specifically, we would like it to be no more than 1. And why exactly 1 we use as a bound, and it will be explained, will be clear later in a short while. So now about WGAN GP, the Wasserstein GAN ingredient penalty. Basically, they suggested a new approach where they want to force the gradient of F to be close to 1 by penalizing the gradient. So the loss function of this Wasserstein GAN with gradient penalty would be the same as a loss function of the WGAN plus some parameter, hyperparameter, times expected value of this expression. It's a norm of the gradient of loss minus 1. So basically, this term will be non-zero and will penalize the loss whenever the norm of the gradient is different from 1. If it's 1 exactly, it's just 0. And by adding this term, we automatically basically require, we don't need basically to every time to clip values after each epoch, which would be a very expensive operation, but just run the training procedure. It will automatically limit the values of the gradient of F. And the suggested value of the hyperparameter lambda is 10. And for that purpose, the authors suggested to use either RMS-prop or Adam optimizer. And finally, the training procedure for the Westerstein GAN or Westerstein GAN with gradient penalty will look like this. We train the critic on real data, require now, this time it's -1, output -1. So as I said, if the gradient of critic is limited by 1, and if we normalize the training data to 1, so basically each image we can divide by the maximum value, so the norm of image will not exceed 1, then we may expect that at the output of critic we should have value between -1 and +1 depending on the sign of the gradient. And this is the procedure modification of the training procedure for regular GAN that we discussed previously. So on the real data, we require that the critic tends to -1. On fake data, it tends to +1. And on the fake data, the W-GAN or W-GAN GP on the fake data tends to -1 again. And when the critic weights are frozen. Any questions? No questions, so I assume it's clear. Now let's discuss the final, what we actually almost the image before the last, I think, the slide before the last one. We'll discuss the RMS-prop optimizer. This optimizer is a particular algorithm that is used to minimize the loss function. And it is based on gradient descent algorithm. This algorithm is wonderful by 2 reasons. First, because it was proposed as an optimizer for training GANs, for example, the W-GAN or W-GAN with gradient penalty. And the second, because this algorithm was proposed by Geoffrey Hinton, one of the fathers of deep learning. It's famous algorithm. It was never published, but nevertheless, it is one of the most widely used algorithms used in deep learning, and it works pretty well. And the description of intuitive description is not easily available. So I wanted here to show some intuitive explanation of what this algorithm is doing. We will start from the basic gradient descent formula, which I discussed in the previous classes. Here, it's basically a formula for updating weights during one step of basically for one epoch or one iteration of update. So the T index, the subscript T is update number. W is a vector of weights, of all weights in the network. Gamma is called the learning rate. It's a hyperparameter. And nabla J is a gradient of loss, a gradient with respect to all weights of a network. So the behavior of why we need RMS-prop could be understood if we consider this particular example, when basically W is sufficient to be 2-dimensional. It's multidimensional, but let's consider for a simple case when there are only two values of two vector of dimension of W is 2. So the loss will be a function of 2 variables. And the surface of loss function will look like this. It will be like a ravine with 2 steep slopes. So the view from above looks like this, where these lines are level lines of the loss function. And we select 2 dimensions, 2 coordinates One is I call long coordinate or L, and the other is short one. The L is directed along the ravine, and the S is in perpendicular direction. And first of all, let's see how the minimization would look if we fix L dimension. We just vary only S, look at only S. So it would be cross sections in perpendicular direction. The J is only, I'm sorry, first look, fix S and look at J as a function of L. The function will look like this, and the gradient is, in this case, gradient of loss as a function of L is small, as it clear from the picture. So in order to ever reach the minimum, which is shown as a red point, we need a large learning rate. Otherwise, we will never reach the minimum. We need large gamma. Now let's look at how things, what will happen if we fix for a while the L dimension, but only look at J as a function of S. In this case, if we still use large gamma, like in this case, then because of the gradient is very steep, we will actually will not reach the minimum, but we will climb up at this large value of learning rate, and we will never get the minimum. So we need smaller gamma. At some moderate gamma, the iterations will still oscillate, but at least at some point they will reach the minimum value. And so basically we cannot, it looks like from this picture, it looks like we ideally would need two different values of gamma. One value, large value, for moving along the low dimension, and the other smaller value, moderate or even small, for moving in the perpendicular direction. And we, of course, we cannot use two different gammas for the gradient descent. It should be one fixed parameter. So instead of two different values, we use one adjustable value, adaptive value, which is proposed by the RMS probe algorithm. So effective gamma that we use, that is used here, will be some constant gamma divided by this expression. And what we have in this expression is a square root of the mean value of the square of the gradient of loss, plus some small parameter, just in case if this term is zero, we don't want to have zero in the denominator. Basically, this expression is roughly proportional just to the gradient of loss. So if the gradient of loss is small, like in this case, it's a shallow gradient, then the value in denominator will be small, and we will have large effective gamma, which we need here in this case, because we need the bigger gamma, the bigger the learning rate, the faster we reach the minimum. However, if the gradient of loss here in the denominator is large, then the effective gamma will be smaller, because the gamma, constant gamma, will be divided by this large value, and the resulting effective gamma will be small, and we will have this case, and so we will go down the gradient in the perpendicular direction. So, but actually, the exact expression in the denominator is a running average of the square of gradient of loss. It is computed as updated as follows. If we have the running average at the previous step, like this one, we multiply it by a certain discounting factor, which is suggested to be 0.9. We take 0.9 with weight 0.9. We take the previous value, of the running average plus unity minus rho, the current value of the square of gradient of loss. And this way we compute the new average value of the gradient of loss. And finally, in Keras, there is a special object or class for computing for the RMS probe optimizer, and the constructor for that class is shown here. In order to create the object, RMS probe object, you need to use this constructor. It passes these parameters. There are more parameters, but only 3 are shown here: the learning rate, the rho, which is the same as in this case, default is 0.9, and the epsilon is this parameter in the denominator. This is basically how the RMS probe algorithm works. Any questions?
I have a question. So a bit kind of confused. So for the low and short coordinates you show in the beginning, don't we use batch normalization to avoid such situation?
No, batch normalization is a different story. Batch normalization, you use it for inside of the network. Inside of each network, you want to basically modify a tensor. Let me see, maybe I'll go back to well, but actually, the answer is no. As I said, batch normalization doesn't help in this case.
Okay, thank you.
What batch normalization is doing, if at the training step, it's not a part of the optimizer. At the training step, if we use a batch of data, which is a number of data items, and we compute a mean value and standard deviation across that batch of data, and then we subtract from each data item. We subtract the mean value of the batch and divide it by the standard deviation of the batch. So basically, for each data item, we make its mean value close to 0 and standard deviation close to 1. But batch normalization, it's just one layer. Basically, it handles only one layer, but the loss is computed as a number of layers in the network. So, well, actually, the answer is no.
So I mean, when you have this difference between your variables, like one has larger variability than another. So
you mean this one and this?
No, like on the top, for example, when you have long coordinate and the short coordinate.
Right.
These are your variables, right? That goes to optimizer.
This I just select the coordinates. If I have this Revin, of course, my weights not necessarily will correspond to this S and short. The weights will be whatever. It may be rotated in any way, but I just select for explanation purposes. I selected this ideal coordinates. One is along the Revin, and the other one is perpendicular to the Revin.
To get an idea, how does that compare to Adam?
For Adam, it's different. Adam is kind of combination of, it will actually discuss in the class number 5, but Adam is kind of, it takes advantage of both RMS probe and of momentum, which we discussed in the previous slide. So it's kind of a combination of the two algorithms with some weights. And it attempts whatever algorithm works better for a particular data, that would be used by Adam. It's hard to say because maybe as a question, I'll open example of the one open slide of the previous of another presentation. Will be easier to comment on Adam algorithm. But for this one, we do not discuss the algorithm is described in class number 5 at the end of the very last slide of class number 5.
Okay, thank you.
If there is no question, I'll proceed to the next slide, which basically describes how we can run BioGAN's application on BioWolf. We first allocate an interactive session. It's not necessarily you can run it on submit a job to cluster, but if you use interactive session, you first allocate interactive session, then you load the model BioGANs, and you can copy data to your current folder from this folder. And the data, that will be data itself plus checkpoints that are already pre-computed. You may or may not use the checkpoints. The checkpoints are saved weights from the previous training, which I already performed. And then there is a number of source files that you can look at by using this command. It's this environmental variable points to the source file folder. And the simplest way to run the training procedure is just say train.py -d and the name of the data folder, which you downloaded from this folder. And that command will use the TC-GAN star-shaped architecture by default, and it will use WGAN GP algorithm for training, which is also default. But optionally, you can use any of these architectures, DC-GAN, DC-GAN separable, and any of this algorithm, just vanilla GAN or WGAN, then with corresponding option. And there are a number of other options also available, but I'll just discuss these as two most important ones. So this is the simplest way of running the training executable. And once after running the training executable, you will generate a checkpoint file, which is file of trained weights. It will be stored in the checkpoints folder. Then you run predict executable and pass it with -i option, a checkpoint file for generator, and it will produce an stack, image stack. And then you can run visualize executable and visualize the images in that stack. And the images, if we use the star-shaped architecture and the WGAN algorithm, output will look like this. So we have a red channel and 6 green channels. All of them are expected to be synchronized. They expected to be corresponding to the same stage of the cell growth cycle, although the stage itself is random. It depends on the distribution of the red channel, which is generated from the noise, and therefore it will be random. So that's basically.
So I think I have a question. So we generated now you have actually basically 7 generators, right? Do you have 7 discriminators?
Yes, six discriminators. 6 for each green channel, we have a separate discriminator.
But you also want a discriminator for the red channel, right?
Oh, it is actually used. The discriminator works basically for a couple. It works on because the images are 2 channels. So yes, okay. Every discriminator will work on double channel image. That's right. So, but each time it will use the same red channel and one of the green channels.
Okay, and then you basically add up the loss of all the 6 discriminators.
And sorry, say it again.
So you basically average the loss of the 6 discriminators in one pass, right?
That's right. That's right. So each discriminator is trained separately. because although we have star-shaped architecture, every time we train only on 2-channel images. And when we train, say, for example, take these 2 channels, then the part of the network of the star, all the ends of the star that correspond to other channels, they will be frozen. The weights will be frozen. Like we discussed previously, trainable equals false, right? So this time we will say trainable equals false for all other channels. Only these 2 will be trained. When we do another training, take another binary image, say, including this red and this green, then this one will be frozen. And every time we do it this way.
Okay. How is that, there is something also called cyclic GAN, which is supposed to like, take one texture and broadcast it in another textures, and it's used in generating high resolution, microscopy images. I'm curious, how this approach compares, because that's what we're trying to do, right? You're getting the red and you want to generate a green, right?
So what is the question?
I mean, I'm just curious how that's different from if you're familiar with cyclic GANs. Just kind of, are you familiar with cyclic GANs?
No, what do you mean?
Oh, it's a different architecture for GANs, like they do, yeah. But that's okay. That's fine. So this clarifies it. Thank you.
Okay.
Excuse me. So for the generator, you need to, like I suggest, you need to generate a random data set, like a 50 random number, like for each of these channels. Then you start to build the image, use a series of up convolution to build up a final generator image.
Right.
So if if I give you the same set of 50 random number, it will up the series of step, it will generate the same image, final image.
If you fix the seed, yes, you will generate the same image. That's right.
Okay, so the final image is totally determined, completely determined by the initial 50 like random data.
Right.
Okay.
Yes.
So usually, like how many such this like generative this noise image you need to generate to train a good model?
I'm not sure I understood the question. How many what?
How many, like, because for the real data, you only have one set of data. But for the random, the noise image, you can generate a lot of them. Many of them.
That's right. That's right.
So how many, do you have like a general idea how many I needed to generate? Then to give them to the discriminator. The discriminator can be trained very well.
We train until we see convergence.
Until we see the convergence.
That's right. There's a lot of data anyway. The number of data I mentioned, 26,000 of images, and we ran train on this data every time we train on batches of data. So we randomly select a subset of images for training, for one step of training. That will be mini batch, and we look at the loss function of the generator loss and discriminator loss, and we see until after it converges. Well, it will not completely converge, but you will see that they do not start at some point, if you're lucky. They do not change much. So you can, I assume that you can stop at this point.
Okay, okay, got it. Thank you.
So for each 6 proteins, you generate different red channel images, right?
That's right. That's correct.
Then you have to synchronize them, basically to compare between different proteins, how they work together.
We assume that they are already synchronized because, as I described, the star-shaped architecture is built in such a way that the green channels are trained to be dependent on the red channel due to concatenation transformation I mentioned previously. So the red channel influences the green, all the green channels. So we expect, it's a reasonable expectation that all the green channels will come up at the same stage of the cell growth cycle as the red channel. And the distribution in the red channel is uniquely linked to the stage growth cycle. It's just the property of that protein. It's a growth marker. So from that channel, expert can figure out what is the stage of the cell growth cycle. But the main point is, even though the red channel generation is random, at least we expect that all the green channels should come at the same stage growth cycle as red channel.
So at one run of the network, you work with all the 6 proteins together or separately?
Right, all together. Depending on what, yes, I'm not sure what you mean by one run, but yes, all together anyway. One run, maybe you mean training step?
Yeah,
or
yes. For
it's
example,
a training step, no. It's a training step.
On your slide 15, when you describe the star-shaped DC GAN,
this one
here, yes. So on the right, so these all 6 green channels are run together or separately, is what I'm trying to understand.
So at the step of training, no. And because at the step of training, when we train, even though our model is star-shaped, but the training data is always 2-channel.
Yes.
Right? So we take 2-channel images. One channel will be a red channel, and the other channel will be one of the green channels. We make active only one of the green channels of the network, and all other ends of the star are frozen for this time, for this particular image. But for the time when we use this particular training input, all the other parameters are frozen. So we train, say, only one type of star, like train it like a separable architecture on the binary 2-channel image. Then we proceed to the next image of training, which may contain different polarity factor, the different green channel, right? Mm-hmm. Then we freeze other subset of, all other will be frozen except the channel corresponding to our training data. And then we train again on binary image with 2-channel image, on 2-channel image only, but all other channels of the star will be frozen.
Okay. Yeah, I'm getting.
So we switch freezing of the weights, temporarily freeze the weights for, basically we have 6 different models for this. We compile 6 different models, which will differ only in the what type of what subset of weights will be frozen, and depending on what kind of input image we have, what green channel is used, we use one of the 6 models, which are already compiled.
Mm-hmm.
Does it explain?
Yes.
Answer?
Yeah.
Yeah.
Okay. Thank you.
Can you go to the small slide?
To the last.
The equation you have, like to compute the distance between the two distribution, like the
Okay. This one, right?
Yeah. So I try to understand at the top, like equation you have DIW equals sigma FIW. So this what does mean I here? W is weight, right?
Are you talking about this equation?
Yeah. This equation.
Okay.
Yeah. W is weight, right?
W is here. Yes.
What does the I mean?
It's a vector of all weights.
Okay.
I is input image.
Oh, I is the input image.
Yes, we take input image as an input. In the next slide, actually, I show a little bit like I here is the same. We take input, some input. The critic takes is input as an image, and it outputs a score. This time it's not probability because it's not between 0 and 1, but some value, some score. Yes, I is input image.
What does mean? You double bar or I mean I is norm?
Double what?
No. Next slide.
Oh, next slide.
Yeah, you for the x-axis, you mean the absolute of I?
Yeah, I'll just show a schematic. I show schematically how the score may vary as a function of the norm of an image. Of course, it's just a schematic picture.
So what does it mean the norm of image?
What, once again?
The norm of image.
Of the norm. The norm, well, for example, in our case, since we the way we do it, say image would be 8-bit image, right? So there would be, for each pixel, we will have values between 0 and 255, right? Because it's 8 bits. So by norm, I mean, in this particular case, dividing all the values of the pixels by maximum value 255. So that's why norm is approximately 1, means basically that the maximum possible value of the pixel will be 1.
Okay.
That's the way we do normalization of the images when we do training. We try to make the norm, the maximum value, no more than 1. It would be equal 1 or less than 1. And the gradient of f is also no more than 1. And this is why in the training procedure, the f itself, which is approximately equal to the gradient of f times the norm of image, will also be limited by 1 in absolute value. It will be +1 or -1 depending on the sign of the gradient. And that's why we require the limiting values in this case would be +1 -1 for the critic, whereas for discriminator, the limiting values were 0 and 1, right? Because it was limited by 0 and 1. Now that's limited by +1 -1. And that's why we change how we change the training procedure.
Okay, thank you.
Okay. Any other questions? And this is a summary, what we discussed in this presentation. We have first discussed a simple introductory section. We discussed a simple GAN example with sequences instead of images. Yes, discriminator was the same as in example of class number 2. Generator network used random noise as input and used transposed convolution to generate real fake data, which in that case was a sequence of zeros and ones. Then we discussed transposed convolution. I did not talk much about batch normalization. Actually, I didn't think that it would be very interesting. It's new type of layer. But if there is a question, I am happy to discuss the batch normalization layer as well. And we discussed train on batch, which is a new type of method for training. It performs training only on one step of training, unlike train or train generator, which is performing all the steps, all the number of epochs. This one is only one step of training. And we use this one because we need to interactively train generator and discriminator. So we train a little bit discriminator and then a little bit generator and stuff like that. And we discussed mode collapse, which occurs, issue that occurs when the training data set comprises not a single type of data, but maybe 2 or more different types of data. Then we discussed BioGAN's application, lean data set of images that we used as input. We discussed different architectures of DCGAN and its possible improvements, DCGAN separable and star shape. Also, we discussed improvements to the discriminator network, discriminator architecture, WGAN and WGAN GP, the Earth movie distance, and the RMS probe optimizer. Thank you. Any other questions and maybe discussions? We are almost run out of time. It's 5 minutes, 6 minutes to 12. So in the remaining 5 minutes, I will be happy to answer your questions if you have any about the software. Although the software is actually, software manual is available on the previous slide, the link here. It should be self-explanatory. And if you can try to run this software. If you have any questions, you can email me. I'll be happy to address your questions about the software.
So just last question, if so, to choose between different architecture, do you usually like try different ones, or you consider your data and maybe questions for what architect you select?
By default, if you run the simplest possible training command, like this one, for example, it will use default architecture and default training algorithm. What's called network model is architecture, and the GAN algorithm, it's just GAN or WGAN GP. Basically, this is refers to generator, and this refers to discriminator. So by default, if you just use this command, then you will use DCGAN star-shaped generator and WGAN GP for discriminator, or critic in this case would be called critic. But if you want to use a different architecture or different algorithm for training, you can specify that with command line options. It's not necessary, but it's optional. For example, you can say -m GAN, and then instead of WGAN GP, you will use the GAN algorithm. So basically, this procedure allows you 9 different combinations, 3 possible architectures of generator and 3 possible GAN algorithms, 9 possible combinations.
So if I work on a new project, like say, so I'm thinking about selecting what type to use. So should I like try everything, or think about like the data and the questions, which architecture will fit better? So
yeah, for a particular data which is different from this data, you may want to experiment with other architectures. Like, for example, for a simple example, in the introductory part, I did not use star-shaped because there was no need in star-shaped. It's overkill. I used just regular GAN and regular DC GAN, and I used regular GAN algorithm. It worked. But for this particular data, I recommend star-shaped and WGAN GP, and this is why they are the default options.
Mm-hmm.
Yes, in general, you can experiment with others as well. They may work. They may work.
mm-hmm. Thank you.
You're welcome. No more questions? Okay, 2 minutes before we finish. So let me, please send me your questions if you have any after the talk, and look at this software. Just we don't have time to run the software anymore. But at least I hope I addressed your questions about the presentation. Yeah, we are done. We're basically run out. So thank you for joining this presentation, and thank you for your questions. We'll keep in touch, and I will let you know when the video is available on our website. I'll send you a message. Thank you.